As the question says, a solid sphere is set into motion on a rough horizontal surface with a linear speed v in the forward direction and an angular speed v by r in the anti-clockwise direction, as shown in figure. Find the linear speed of the sphere A when it stops rotating and when slipping finally ceases and pure rolling starts. Now, if we look at this point A, which is in contact with the ground, then we are having anti-clockwise velocity. So here we will be having a velocity omega into r, that is v to the right, and it is itself moving with the velocity v. Hence, the velocity of this part becomes 2v forwards, and hence it slips on this surface, which produces a frictional force F in the backward direction. So ultimately what happens is that once it will stop slipping, that is, it will be now this, that it will be only having a anti-clockwise rotation, and the velocity of this center of mass, it will stop slipping, but it will be having some velocity v naught, and it won't be rotating at this, and then this will further change into a situation in which it will be like this. It will be having a velocity v dash, and it will be rotating with some rotational velocity, right? So now let us see, if friction is acting along this surface, then the torque along this point will be 0, right? So if external torque about point A is 0, then let us conserve the angular momentum about this point, right? So for that, we can write down it as the total angular momentum before and after is going to be the same. So we can write it as, afterwards we are having an angular momentum of m v naught into r, right? Because this is v naught and the distance is simply r, so it is m v naught r. And we all know that L is about L center of mass, that is L of the whole body with respect to center of mass, plus the L of center of mass itself, right? So here we will be writing it as mv naught r. Now the angular momentum of the body about the center of mass. Now mv naught here is in clockwise direction. You can see it like this. V naught cross r is clockwise, because if you take this point and apply this, then this will be rotating in the clockwise. So it is in clockwise direction. Due to the rotation that is about the center of mass, it is in anti-clockwise direction. So we will be writing it as minus 2 by 5 I omega, that is 2 by 5 mr square into v by r. And further, due to this constant velocity, it is in clockwise direction, so we will be adding it up with mvr. From this we get v naught equals to 3v by 5. So this is this velocity which with which it will be actually moving once it stops rotating. So this is the answer for the A part of this question. Now let us proceed to the B part, in which we need to find out when finally the slipping ceases and the pure rolling starts. Pure rolling start means that this point is at rest with respect to the ground. So if v dash is in forward direction, then the v dash will be in opposite direction due to rotation itself, so as the velocity of this point becomes 0 with respect to the ground. So now we are employing the same thing, that is conserving the angular momentum about this point, and which will be like m v dash r, because since it is in clockwise direction, we are going to add up that of the whole sphere about the center of mass, which will be 2 by 5 mr square into v by r, and this will be equal to the initial angular momentum, which will be m v naught r. Now friends, in these cases we are not taking with respect to the center of mass because this sphere is actually not rotating. So no use of taking about the center of mass if the body is not rotating. So it will be simply acting as a normal block going ahead with the velocity of v naught. So that's why there is no angular momentum above the center of mass being taken in this equation. Now from here we can calculate v dash to be 3v by 7. So this is the answer of the B part of this question. That is when it starts pure rolling. And friends, in this equation, when we frame this equation, this V by R, V has to be of this because we are taking about the center of mass. So it has to be V dash, right? Now here since we have conserved the angular momentum and we have equated it with mv naught r, you could have directly equated it with this thing because this thing is already equal to this. So we are having the three situations. You can conserve this angular momentum about this point in any of the two things. That is the two cases.